This is mixed exercise 9.01, and this is on differentiation, pure maths year 2. We're going to answer 3 questions. Question 1. Given that y is equals to all that, find dy dx when x is equals to 0. I'm going to use 2 methods to answer this question. For the first method, I'm going to use implicit differentiation, and then I will use quotient rule for the second method. So first method, I'm going to take logs of both sides of the equation. So if I do that, I'm going to get ln y is equals to ln 1 minus x squared brackets e to the power minus x over 1 plus x squared. Then I'll use the laws of log to simplify the right-hand side of the equation. So I have ln y is equals to ln 1 minus x squared e to the power minus x. I close my square bracket minus ln 1 plus x squared. I'll continue to simplify this term using the laws of logs again, and I'll get ln y on the left hand side equals to ln 1 minus x squared plus ln e to the power minus x minus ln 1 plus x squared. Then I will simplify this term here, and I'm going to get ln y is equals to ln 1 minus x squared minus x, because ln e to the power minus x will give me minus x, minus ln 1 plus x squared. I can now use implicit differentiation to differentiate all that as follows. For this, I'm going to use chain rule, and that will be 1 over y dy dx, because if I differentiate ln y, I'm going to get 1 over y, and I'll differentiate y to get dy dx. That will be equals to 1 over 1 minus x squared times the differential of this one, which will be minus 2x. Then if I differentiate minus x, I get minus 1. And I'll differentiate this term, I'm going to get minus 1 over 1 plus x squared. Then I'll differentiate this one as part of the process of chain rule, so times 2x. I can now write this as 1 over y dy dx equals to minus 2x over 1 minus x squared minus 1 minus 2x over 1 plus x squared. So now I want dy dx. So I'll take y over to that side to multiply the whole of this term, and I'm going to get dy dx equals to y brackets minus 2x over 1 minus x squared minus 1 minus 2x over 1 plus x squared. But we know that y is equal to all that. So I will substitute this fraction over here to get the following. So dy dx is equals to 1 minus x squared times e to the power minus x over 1 plus x squared. So all of that times minus 2 x over 1 minus x squared minus 1 minus 2x over 1 plus x squared. So that's the differentiation required, but we're looking for the value of dy dx when x is equal to 0. So when x equals to 0, dy dx is equal to, that will be 0, and that will be 1. So 1 times 1 will be 1. So I'll have 1 times 1 over, if I put 0 here, the whole denominator becomes 1. So this will be multiplied by, if I put 0 here, the whole thing becomes 0. So that will be 0 minus 1. And if I put 0 here, I get 0 as well. And so the whole differentiation becomes 1 times minus 1. And finally, we get minus 1 as our answer. And so that's the value required. Now, I'm going to use the quotient rule. The quotient rule states that if you got y equals to u over v, then dy dx is equals to v du dx minus u dv dx over v squared. So we're going to use that to do this differentiation. So I'll say let u equals to 1 minus x squared times e to the power minus x, and therefore v equals to 1 plus x squared. So du dx will be equals to, and this is why I keep one of these things constant and differentiate the other. So if I keep e to the power minus x constant and differentiate this, I'm going to get minus 2x e to the power minus x. Then I'll keep this constant and differentiate e to the power minus x. So that will be 1 minus x squared, all in brackets, times the differentiation of that. That will be e to the power minus x. And this is negative because when you differentiate e to the power minus x, you get minus e to the power minus x. And that's why this is negative, because I'm using the product rule here. So now I've got du dx as that. Now I need to do dv dx. So dv dx is equals to 2x. I would like to simplify this one to make things easier. So I can factorize e to the power minus x out. So I can do minus e to the power minus x comes out, and I'll get 2x at this side, and I'll get plus 1 minus x squared over here. Then I close my square brackets. And so now I can go and apply this rule here. dy dx is equals to v du dx minus u dv dx, all of that over v squared. But v is this, and du dx has been simplified to that. Also, u is this, and dv dx is 2x. So if I do my appropriate substitution, dy dx becomes 1 plus x squared, which is v, times all this, which will be 2x minus x squared plus 1 times e to the power minus x. But there's a negative here, So I prefer to put a negative over here. And then minus u dv dx. U is this one here, and dv dx is that. So I'm going to get 2x for this one, and then times the u, which will be 1 minus x squared multiplied by the e to the power minus x over 1 plus x squared, all of that squared. But instead of simplifying this, we are just told to find the value of dy dx when x equals to 0. So when x equals to 0, dy dx is equals to, now we'll do our substitution in this. So if I put 0 here, I'll get minus 1. So I get minus brackets 1 plus 0. If I put 0 here and 0 there, I get 1. So that will be 1. If I put 0 here, I'll get 1. So that will be times 1 minus. If I put 0 here, that will make the whole of that 0. So that will be minus 0. So all of that over. If I put 0 here, I'll get 1 here, and that will be 1 squared. So that will simplify to dy dx is equals to minus 1 minus 0 over 1 squared. And then we get minus 1 as our final answer. Same as what we got over here. So that's question 1, done in 2 different ways. And as you can see, we got the same answer. Question 2. Find an expression in terms of x and y for dy dx, given that a. X to the power 4 minus y to the power 4 is equal to 2xy. B. X squared plus 6xy plus y squared equals to 5. So for these 2 questions, we need to use implicit differentiation. So for A, I've got x to the power 4 minus y to the power 4 is equals to 2xy. So I'll start differentiating. If I differentiate x to the power 4, I'm going to get 4x cubed. Then I'm going to use chain rule to differentiate this term, and that will be minus 4y cubed. Then I differentiate the y itself, I get dy dx equals to, then I'll use product rule here, because this is the product. That's 2x as one function and y as another function. And the product rule says this: if you've got y is equals to one product times another product, u and v, then dy dx is equals to u dv dx plus v du dx. So I'm going to use that. So the process here is simplified. Think of it this way. Keep u constant, differentiate v together, and then keep v constant and differentiate u together. And so that's what I'm going to do for this product here. So now I'm going to get, keeping 2x constant, get 2x, and differentiating the y, get dy dx, plus, keep the y constant this time, and differentiate 2x. So if I keep the y constant, and differentiate 2x, I get 2. So that is the differential of this term here. Now I'm going to simplify by dividing every term by 2. If I do that, I'm going to get 2x cubed minus 2y cubed dy dx is equal to x dy dx plus y. Then I will bring like terms together. and get the following. 2x cubed minus y is equals to x dy dx plus 2y cubed dy dx. Then if I factorize the right hand side, I'm going to get 2x cubed minus y is equals to x plus 2y cubed dy dx. Then I can make dy dx the subject by rearranging, and that will give me dy dx is equal to 2x cubed minus y over x plus 2y cubed. And that is the required differentiation for A. For B, so I've got x squared plus 6xy plus y squared equals to 5. I have 2x plus, and this is the product. So I'm going to use product rule here. First, I'll keep 6x constant and differentiate y, and then I'll keep y constant and differentiate 6x. So I have keeping 6x constant, I'll get 6x. Differentiating y will be dy dx. Next, I'll keep the y constant, so plus, keep the y constant, that will be y, and differentiate the 6x, you get 6. Plus, use chain rule to differentiate y squared, I'll get 2y dy dx is equals to, if you differentiate 5, because it's a constant, you get 0. I'm going to divide every time by 2 to simplify the equation. If I divide by 2, I'm going to get x here plus 3x dy dx plus 3y plus y dy dx equals to 0. Then I will put like terms together, and I'll get 3x dy dx plus y dy dx is equal to minus x minus 3y. Factorizing the left-hand side, you're going to get 3x plus y brackets dy dx equals to minus brackets x plus 3y. I can now make dy dx the subject to get the following. Dy dx equals to minus brackets x plus 3y over 3x plus y. And that's the required differentiation. Question 3. Show that the normal to the curve y equals to tan x at the point A with coordinates pi over 4 and 1 meets the x-axis at the point B with coordinates pi plus 8 over 4 and 0. So I've got y is equal to tan x. I need to differentiate to get a gradient function. So if I differentiate dy dx is equal to sec squared x, which is equal to 1 over cos squared x. But when x is equal to pi over 4, then the gradient function dy dx is equal to sec squared pi over 4, which in turn is equal to 1 over cos squared pi over 4. But cos pi over 4 is equal to root 2 over 2. So it means this will be equal to 1 over root 2 over 2 all squared, which is the same as 4 over 2. And 4 over 2 is 2, so we can say that the gradient of the tangent to the curve at A is equal to 2. That means the gradient of the normal at A is equal to minus 1 over 2. Therefore, the equation of the normal at A is given by y minus 1 over x minus pi on 4 is equal to the gradient, which is minus 1 over 2. So if I cross multiply, I'm going to get 2y minus 1 is equals to pi on 4 minus x. If I expand the left-hand side, I'm going to get 2y minus 2 is equals to pi over 4 minus x. Then I'm going to rewrite this equation appropriately to get 2y plus x is equals to pi on 4 plus 2. But at the point B, y is equal to 0, because that's where it casts the x as is. So substituting 0 into this equation will give you 0 plus x equals to pi over 4 plus 2. So x is equals to pi over 4 plus 8 over 4, which is 2. And that will give you pi plus 8 over 4. Hence, coordinates of B is pi plus 8 over 4 and 0. And this is the proof required. And this brings us to the end of this session on differentiation.